All right, we're covering inverses and determinants. Now, before we go on to inverses and determinants, we need to cover something called the identity matrix. So let's discuss the identity matrix. The identity matrix is a special type of square matrix. It's a square matrix. All of its entries on the main diagonal are 1. And the main diagonal is something new that you'll encounter. So the main diagonal runs from the top left of a matrix to the bottom right of that matrix. All other entries in the identity matrix are 0, and I'll show you what a main diagonal looks like. So the identity matrix is denoted by IM, so I subscript M, and that has the dimension M by M. Remember, it's a square matrix, so the number of rows it has must be the same as the number of columns that it has. So IM, it's a square matrix, the identity matrix, a square matrix with dimension M by M. And in some contexts where the dimension is understood, that means we can kind of gauge or understand the dimension just by looking at a problem or by looking at the context, then the identity matrix is denoted by I. It's just simpler to denote because we'll understand what the dimension needs to be. We can work it out. So below are some examples of the identity matrix. Here we have an I'm just going to say it as I2. So here's I2. It's a 2 by 2 square matrix. And the main diagonal, here's the main diagonal. It runs from the top left here to the bottom right. It's a diagonal of a square matrix. So it has to be, its position has to be diagonal basically. And it's from the top left to bottom right. So there's the main diagonal. You can see all the entries there are 1, and all the other entries that are not on the main diagonal are 0, right? So that's the identity matrix with dimension 2 by 2. Here's I3, so again, here's the main diagonal, top left to bottom right. So let's circle those entries. There we go. We can see that everything on that main diagonal is 1. All the other entries are 0, right? So that's I3. And here's I1. Well, the main diagonal, top left to bottom right, let's me circle that. It's only that entry, so it has to be 1. So that's the I1 matrix. So why am I telling you this? Why are we doing this before inverses and determinants? Why is this identity matrix of any importance? So the identity matrix can be thought of as the number 1 of matrices. So just like how you have the number 1 for the real numbers, the identity matrix is kind of like the number 1 of matrices. And you'll see why when I show you these important properties. So below are some of the important properties of the identity matrix. So if A, so we're going to consider this general matrix A, and it's M by N. So it has M rows and N columns. Then you take A, so A is, remember, M by N, and then you're going to multiply it by the IN matrix, the N dimension identity matrix. That's N by N. So we can multiply these N by N. The resulting matrix is going to be M by N. And I gave you a hint. The identity matrix is like the number 1 of matrices. So if I multiply A by IN, I'm going to get the matrix A back. And I'll show you why this is so when we do some examples, right? And I can also we can do it in the opposite order. So I could take the identity matrix first and multiply it by A. So A is M by N. In order for this multiplication to work, I need to have an M by M identity matrix. So that's IM. M's are the same. So my resulting matrix is going to be M by N. And it's no surprise that it's going to be A. So that's why it's like the number 1 of matrices, because if you take a matrix and multiply it by the identity matrix, you're going to get that matrix back. The same thing works if you have the identity matrix first and multiply it by any matrix A, you're still going to get that general matrix A back. So that's why I hope you can see it's like the number 1 of matrices. All right, example 1. So we're going to find the identity matrix, and for the identity matrix, I'm just going to say I. We're going to find IA and AI, and we're given the matrix A. So let's find IA first. That means matrix A is going to be the second matrix that we multiply, right? And matrix A is a 3 by 2 matrix. So to get a suitable dimension for the I matrix needs to be 3 by 3. This 3 has to match with that, and because the I matrix is square, that obviously also has to be 3. So we're going to use an I3 matrix. So the I3 matrix looks like this. It's 1, 1, 1. That's its main diagonal. All the other entries are going to be 0. All right, here's the I and A matrix. Let's do the multiplication. So we have a 3 by 3 multiplied by a 3 by 2. The resulting matrix is going to be 3 by 2, and we expect to get the A matrix back. I'm just going to do a bit of the multiplication to show you that we do in fact get the A matrix back. So we get a 3 by 2, that's 3 rows, 2 columns. All right, let's work out the entry in the first row, first column. So first row, first column, we'll take 1 times by 4, that's 4, and then we have 0 and 0 times by 3 and 10 respectively. Those are all 0, so we'll have 4 plus 0 plus 0, that's 4. Then we're going for the first row, second column, 1, 0, and 0 times by minus 3, 5, and 0. When you do that multiplication, you're going to have 1 times minus 3, that's minus 3, plus 0, so that's minus 3. And then you can go ahead and complete this multiplication to go to 0 there. So you'll take row 2 times by column 1 of this matrix to get this entry, and you should expect to get 3. And I'm sure you can see the pattern now. Because you have those zeros in those off-diagonal positions, whenever you're performing the multiplication, you'll always have the 1 times by the entry that you want in the respective entry for your resulting matrix. So if I had to complete this, it's no surprise I'm going to get 5, 10, and 0, the A matrix back. And what I encourage you to do is get A times I, so A times the identity matrix, and I'll just help you there. So you can take this out. Right, so in this case, you'll have a 3 by 2, and now you need to multiply it by an identity matrix. So the identity matrix dimension you need to work out. You have a 2 here, so you need a 2 by 2 identity matrix. So this 2 and that 2, those are going to match. And the identity matrix is square, so that obviously has to be 2. So we're going to be using a 2 by 2 identity matrix. So 1, 1, 0, and 0. And then I encourage you to, again, multiply this out. You're going to get a 3 by 2, so 1, 2, 3, 1, 2, 3. And you should expect, or we are guaranteed to get this A matrix back. So do this multiplication, you should get 4 minus 3, 3, 5, 10, and 0. Right, so that's why the identity matrix is like the number 1 of matrices. All right, now that we've covered the identity matrix, we are now in a position to understand inverse matrices. So only square matrices can have an inverse matrix. So those 2 by 3, 5 by 7, 8 by 10, those are not square. They cannot have an inverse matrix. Only square matrices, 2 by 2, 3 by 3, 4 by 4, etc., can have an inverse matrix. If a square matrix A has an inverse, the square matrix is said to be invertible. So if I have a matrix A and I tell you, hey, this is invertible, I'm basically telling you this matrix has an inverse. So what's an inverse? Let's consider the square matrix A, and that is n by n. If there is a matrix denoted by A and the superscript is -1, but we read it as inverse A, I'll just give you an analogy of why we have that superscript as -1. So if there is a matrix denoted by A to the A superscript -1, so that's inverse A, such that A multiplied by inverse A is equal to the identity matrix. So we can also have inverse A multiplied by A, and that will be equal to the identity matrix. If that relationship is true, then this is called the inverse matrix of A. So what does all of that mean? This is the inverse matrix. When you take the inverse matrix and you multiply it by the original matrix, you're going to get an identity matrix. It doesn't matter in what order you multiply them. They are both square. They are both n by n. So the order in which you multiply them really doesn't matter. You can even take the inverse first and multiply it by the original. You'll still get an identity matrix. More specifically, you'll get an n by n identity matrix. Now let me explain or give you a bit of an analogy about why that superscript is -1. So remember I said that the identity matrix is kind of like the one-off matrices. So let's consider numbers. What happens when you take 7 and multiply it by 1 over 7? You get 1, right? 1 over 7, we can write that as 7 to the -1. So now replace the 7's with matrices A, and replace the 1 with the one-off matrices. There we go. Okay, so that's kind of why you have that superscript as -1. So note that the inverse matrix A is unique. This basically means that a specific invertible matrix A only has one possible inverse matrix A. So if I give you a certain matrix A, it's only going to have one possible inverse. Let's say the inverse, and I'll show you how to get the inverse in a while, just now. So let's say the inverse, I'm just making stuff up, 2, 5, 3, 1, right? It's not like this is the first possible inverse, and then there's another one where we could have 7, 0, 6, 1, another possible inverse. If this matrix A here, the original, has an inverse, it only has one unique possible inverse. There's no two possibilities or three possibilities or 10 possible inverses. There's only one single inverse if that original is invertible. In some cases, a square matrix may not have an inverse matrix, right? If this is the case, it is said to be non-invertible or singular. So if it has an inverse, then okay, it's going to be invertible. The matrix A, the original one, is said to be invertible. If it doesn't have an inverse, then it's non-invertible. Another way that we can say non-invertible is singular. And how I like to remember this, here's my original matrix. If it doesn't have an inverse, its partner, then it's single, right? It doesn't have a partner, so it is singular. And similarly, if it is invertible, we can say it is non-singular. So here's my original matrix A. It's invertible, that means it has an inverse, its partner basically. So it has a partner, it's not single, it's non-singular. So that's just terminology that you need to get used to. So you recognize all the different ways of understanding, okay, this matrix has an inverse, this matrix does not have an inverse, etc. So just to summarize it, a square matrix that has an inverse, it's going to be invertible because it has an inverse. It has a partner, so it's not single, it's non-singular, right? A square matrix that has no inverse, doesn't have an inverse, that means it's non-invertible. Since it doesn't have an inverse, it doesn't have a partner, that means it's single, it is singular. So just beware of this different terminology. Don't confuse them and remember the techniques I'm telling you to remember it. So given the original matrix A, here we have matrix A, I want you to verify that the inverse matrix, and I've given you inverse A, so I want you to actually verify that that is the inverse matrix. So how are we going to handle this example? Well, if this is in fact the actual inverse, then the original matrix A multiplied by this supposed inverse should give us an identity matrix I. If this is not the inverse, then we'll get something that isn't the identity matrix. We'll get some other nonsense. So take a minute and try this example. Also, you could even do the inverse times by matrix A, and you'll still get the identity matrix. Remember, it doesn't matter in what order you multiply it, but what I'm going to do is I'm going to find A times the inverse. So pause the video, try it. All right, let's go for this example. So we're going to have my original matrix here, 2, 1, 2, 1, 3, 2, minus 1, 1, and 0. And then we're going to have the inverse minus 1, 1, minus 2, minus 1, 1, minus 1. And let's complete it. There we go. Right, so let's do this multiplication. They are both 3 by 3. So we expect to get a 3 by 3 matrix, and we expect to get the identity matrix. So 1, 2, 3, and here are my entries. Let's deal with the first entry. So it's going to be row 1 times by column 1. So it's going to be minus 2. I'm just doing the multiplication mentally. It's going to be minus 2, minus 1, and 4. Add those up, we get 1, which is what we expect. Then we are going to do row 1, column 2. So we're going to do it mentally. We're going to get 2, 1, and we're going to get, let's check, minus 3. 2 times minus 3 over 2 is minus 3. Add those up. Surprise, surprise, we get 0. Then row 1, column 3, we're going to get minus 4, minus 1, and 5. Add those up. No surprise, we get 0. Excellent. Let's go for row 2, column 1. So we're going to get minus 1, minus 3, 4, 0. The next one, I expect to get positive 1. So let's check. We're going to get 1, 3, minus 3. Add those up. There's our 1. And then we're going to get minus 2, minus 3, and 5, 0. All right, one more row. So row 3, column 1, we're going to get 1, minus 1, and 0. That's 0 when you add them up. Then we're going to get minus 1, 1, and 0. That's 0. Last one, let's hope it's 1. So it's going to be 2, minus 1, and 0, and ta-da. There we go. So if you take a look at this closely, let me get rid of these lines. What do we have here? So we have an identity matrix because everything on the main diagonal is 1. All other entries are 0. And this is an I3 identity matrix, a 3 by 3 identity matrix. So this, in fact, is the inverse matrix. What I advise you to do is find inverse A multiplied by A and check that you can get the identity matrix just for some practice. You are going to get the exact same identity matrix. All right, that's example 1. So all this talk about inverse matrices, that's great. How do we actually find the inverse matrix? Because that's what we actually want to do. So let's go for method 1. Now there are multiple ways to find the inverse of a square matrix. However, the following method to find the inverse, that's method 1, it's one of the easiest to understand. So it's one of the easiest methods, but it is a lengthy process. So I think it's one of the easiest ways to comprehend it, but it is a bit lengthy. So you can examine the different methods and check what you want to use. I like using method 1. So I'm going to go through the rules, and it's okay if you don't understand the rules because you're going to understand them when I do an actual example with you on the next screen. So first step, given the square matrix A, write it in an augmented matrix A, and then you're going to put a vertical line, and then you're going to have an identity matrix that corresponds to this A matrix. Basically the same dimensions. That's what I mean by correspond. Step 2, you're going to use elementary row operations to transform A into an identity matrix. Remember to perform these row operations on the right-hand side of the vertical line. The resulting matrix on the right-hand side of the vertical line is the inverse matrix of A. Note that if you cannot transform A into an identity matrix, then the matrix is not invertible. So it may not make a lot of sense right now by me just reading this out, but let's go for an example and you'll see how easy it is. All right, exercise 1, find the inverse matrix of this matrix A if it exists, and I can tell you now it does exist. Don't worry, later I'll tell you how, or I'll tell you the technique of finding out whether a square matrix is invertible or not. It's super easy, but right now let's stick to finding inverses. If you want, pause the video and you can try it on your own. Right now I'm going to do the solution. Okay, let's go for the solution. So step 1 is to take this square matrix A and write it in terms of an augmented matrix like this. What this means is make a big augmented matrix. On the left hand side, write down your original matrix, 2, 7, and then on the right hand side of this vertical line, write down the corresponding identity matrix. So this was 2 by 2. I obviously need a 2 by 2 identity on the right hand side of this vertical line. That's step 1. Right, let's just shrink this. There we go. Step 2 is to use elementary row operations to transform this into an identity matrix. So what we mean is this needs to be 1, that needs to be 1, and all the other entries of the main diagonal need to be 0. So this is how you do it. What I'm going to do is, firstly, I'm going to leave row 1 as is, okay? And then I'm going to take row 2 and minus 2 times row 1. So row 2a is equal to row 2 minus 2 times row 1. Remember, when you are doing these elementary row operations, I advise you to write out what operations you are using, so whoever is checking your work can follow along and see your thought process clearly. I'm not going to write this out for the lack of space. I'll explain what I'm doing as I go along. So it'll be 2 times, it'll be 2 minus 2 times 1, that's 0. 7 minus 2 times 4, that's minus 1. 0 minus 2 times 1, that's minus 2. And then 1 minus 2 times 0, well, that's just 1. All right, there we go. Now I want to make this minus 1 positive 1. So I'm just going to multiply this row 2 by negative 1. So there we go. That's how we do it. We multiply it by negative 1. Then to transform this into identity, I just need to make this 4 into a 0. So I'm going to take row 1 and minus 4 times this new row 2. So my row 2 is going to remain as is. It's going to be 0, 1, 2 minus 1. And then I'll take 1 minus 4 times 0, and that is 1. 4 minus 4 times 1, that's 0. There we go. Look at that. Then it's 1 minus 4 times 2, that's minus 7. And it's 0 minus 4 times minus 1. Be careful there, it's positive 4. Notice how whatever operation I was doing on this matrix, I had to do it on the right-hand side of the vertical line. Right? So remember to always perform your row operations on the right-hand side of this vertical line. Remember, this is one augmented matrix after all. Now, here's the answer. A was this matrix here. There's it there. Now that we have transformed this into identity matrix, my inverse is this matrix here. There we go. So it's minus 7, 4, 2, and minus 1. That is your inverse matrix. And again, what I'm going to encourage you to do is take this matrix here, this inverse A, and multiply it by your original matrix A. Check if you do in fact get an identity matrix. If you do get an identity matrix, great, then you found the inverse. If you don't, then there's one of two possibilities. One, this is not actually the inverse and you made a mistake somewhere in your row operations. Or two, when you are multiplying the inverse by your original matrix, then you made a mistake with the multiplication. So just go back and double check your steps. But this is the inverse matrix.